Okay, so what we would like to do is we would like to have a combined theorem that goes. Okay. So we'd like to have a combined theorem that goes from a discrete set of backward SDEs, and then it takes you directly to the continuous time McKean, to this continuous time limit down here. It is coming from my own device. That's the problem. Okay, so maybe now it is better, at least this thing. Okay, so the first point I would like to make is that, well, we don't want to consider forward SDEs, we want to consider backward SDEs. So I would like to argue that backward SDEs are a very natural object in mathematical finance. So, well, let's do it for the slide as it is a bit simpler. So let us just take a simple model for the evolution of a financial asset, right? We have a forward SDE starting from some point little x, and this gives you how the price of some asset evolves. Then you consider a financial derivative. So a financial derivative is a legal contract that says that at some time point in the future that we call capital T, the two parties involved in the contract are going to exchange a payoff, which is denoted by this f of ST. Okay, and then from mathematical finance theory, we know that we can compute the price of this derivative, and the price of this derivative is given by the conditional expectation of the payoff. But now, I mean, if you take some integrable random variable and you condition it and take the expectation, then you are creating a martingale, right? This is easy. And well, if this is a martingale, and then we assume that we are in a filtration, that it is, I don't know, generated by the Brownian motion up there, well, then this should have a martingale representation, right? So I should be able to find some process. I should be able to find some process Z such that this equation holds, right? Okay, everything is simple here. The only issue with this equation is that in this equation, we don't know the initial value. This is actually what we are interested in math finance theory. We only know the terminal value. So if we just use the fact that we know what the terminal value is equal to, and then we rearrange everything appropriately, we arrive at a prototype of a backward SDE. So this is basically an SDE of this form where you know the terminal condition and you don't know the initial condition. Okay, so this is how an SDE looks like, BSDE looks like. Okay, this is of course a very simple object. We know how to compute analytically, so we never bother, treating this as a BSDE. But this was just to show you why this is arising naturally in math finance. Okay, so more complicated versions of BSDEs appear in this classical framework of Pardue and Peng, and then also El Karoui, Peng, and Kenes. And the main setting is the following. So you assume that you have some filtered space, you have some given finite time horizon, and then you basically assume that some things are known, and the known things, they are denoted in this slide by green, and they are the standard Brownian motion, which is driving the BSDE, this terminal random variable, and the function f. And then you write a general BSDE in this form that you have the terminal condition, plus you have some finite variation term, and then you also have this martingale term. Okay, so the known terms are denoted by green, the solution is denoted by red, and the solution is the BSDE and this the integrator you're looking for here. Okay, yeah. Depends what you want to do, right? I mean, in the classical setting, it is just it's just Lipschitz. You can also make a stochastic Lipschitz in some cases.
So I was wondering because
or it is copied from some other slides where it is stochastic. Okay. But you can do a lot of things, right? Good. Now, if you're not so much into BSDEs, or if you really like PDEs, there is a very interesting nonlinear version of the Feynman-Katz formula that tells you that if you consider a system of a forward and a backward SDE, where the forward component is more or less what we had before, and the backward component was what we had in the previous slide with some terminal condition, then you can associate this with a solution of a quasi-linear PDE where the term here is the infinitesimal generator of the diffusion process, the X diffusion process. Here you get this, this drift term from the BSDE, and here you have the terminal condition. Okay, so you can also associate forward-backward SDEs with nonlinear PDEs, and then you can solve whichever is more convenient for you. Okay, so what do we want to do? We were inspired a little bit by this guy. So this guy is called Jacques Hadamard. He was a mathematician living in the previous century, or maybe 2 centuries ago. And he had a very interesting treatise about equations in mathematics in general. And he said that an equation is well posed if you can prove 3 things about this equation. That a solution exists, that a solution is unique, and also if you have some sort of continuity or between the initial conditions and the output. So what we would like to do is we would like to consider BSDEs driven by general semi-martingales. This is a little bit the novel part, and then also show that you can basically go through with Hadamard's program, so existence, uniqueness, and then so stability, but then stability is a little bit more general than what you were saying. So you also want to prove stability from like discrete time to continuous time equations. Okay. So let us see how we can try to go to a more general and a more unified framework. So BSDEs driven, for example, by Levy processes that were considered in papers by Tang and Li, and also Bar, Buktan, and Pardue. And the setting is more or less the same as before. So you have a filtered space, you have some terminal condition, you have some Lipschitz function, and now you replace the Brownian motion by a Levy martingale. So you have a diffusion component and you have a purely discontinuous component. And then, of course, the form of the BSDE changes a little bit. So you have an integral with respect to your continuous martingale part. You have an integral with respect to the jump part. You have this finite variation part in the terminal condition, but you can more or less carry through with the same program and prove existence and uniqueness results. Okay. So if you want to consider more general semi-martingales, the idea is the following, right? You're going to replace here the Levy martingale by some general semi-martingale. And then, if you don't have the predictable representation property, okay, whatever that is now, then you will probably need to add one more term here. Okay, this is fine. I mean, you just need the whole set of martingales that span your the space of martingales. The difficulty a little bit is arising if you want to consider discrete and continuous processes in one framework. Okay, if you want to consider discrete and continuous processes in one framework, of course, you can replace this with some discrete time process, and you can replace this with some discrete time process, but then you cannot integrate with respect to ds, of course, because this is not a natural compensator for a discrete time process. Okay, and here there is a very nice tool from stochastic calculus, which is called semi-martingale characteristics, that could come to your help. So, okay. Okay, so let's look first of all at Levy processes. So I think everybody knows in this audience a little bit about Levy processes. So you have basically 3 main characterizations of Levy process. You can characterize the path from the Levy to decomposition, and they tell you that you can decompose the path into a drift term, a continuous martingale part, which is Brownian motion, and the pure jump part, which is martingale. You can characterize the law by the Levy-Khinchin representation, and you can also describe them, well, locally, but then also both globally. by this Levy triplet. Okay, and you see that the triplet is appearing everywhere. Okay, it's appearing in the decomposition and also in the representation of the law. Okay, so now I can try to change to this thing if I am successful. Okay, well, it works. Okay, so let's look again at this is how your Levy process looks like. And here you have this integral with respect to the pure jump martingale. Okay, and now imagine that you are taking things step by step. So you have now a process which does not have stationary independent increments. It has only independent increments, but then the coefficients can depend with respect to time. So what you would get here is basically you would get locally some characteristics that depend on the time. So the way you would be able to describe the path in the same way is, well, here you would integrate from 0 to t. And then with respect to Lebesgue, and here you would also integrate from 0 to t. And more or less nothing has changed, right? And then you can, well, you can replace the Levy triplet by a triplet which is the integral from 0 to t of these coefficients and the integral from 0 to t of these coefficients, and you can do something similar here. Okay. So if you have a process which has independent increments but non-stationary, you replace the martingale, the Levy triplet with this triplet. Okay, fine. And well, you can do the same thing if you also have a general semi-martingale. So if you have a general semi-martingale, you would still represent it in the same way, integral from 0 to t of PS. And now this will depend on omega as well. It will be random. And here you would get something similar. Okay, and so on. And then you would still be able to describe like globally the behavior of this process by looking at this characteristic. So you would look at this, and then you integrate the S, and so on, right? I think you get the idea. Okay, so yes. The WS, I mean, this is the integral with respect to Brownian motion or some continuous martingale in general. In general, yes, here you would have something like the continuous part of this martingale. Yeah. Okay, and then okay, but now if you want to encode also, in this setting a discrete time process, you can still describe it in the same way. It will behave locally like a drift part, and then you would have something like a continuous martingale part, and so on. And the only thing that you would need to change is that then you cannot integrate with respect to Lebesgue any longer, but you would have to integrate. You would have to integrate the local behavior with respect to some process which is predictable, increasing, and Cadillac, but not continuous, right? Okay, so this allows you to describe discrete and continuous processes in one setting by just looking at the local behavior and then a process which is essentially the finite variation of whatever you have. So now I want to go back to the original slide somehow. Okay, thank you. Thank you very much. Okay. Okay, so now if you want to describe then a general semi-martingale, you can do it by just describing like the local behavior of the process and then something like the quadratic variation of whatever martingale you have. And then you can create funny examples like the one that Jan Carlsen did in his thesis, and he calls it, I don't know, extended Grigelioni's martingale for whatever reason. This is basically a superposition of a Levy process with a random walk. And the whole characterization is basically that telling you that you have to take, the rate of increase is Lebesgue measure plus the times at which the random walk is jumping. Okay, so this is a nice framework where you can describe everything in one go. Okay, so I think now we have all the tools that we need in order to describe general BSDEs. Okay, so again, for general BSDEs, green is the data that you are given, everything that you know from the beginning. The red is the solution. So here we consider a square integrable martingale, which can be stochastically discontinuous. So we have discrete and continuous processes in one go. And this X with this circle, it will correspond somehow to whatever will be in the limit, a continuous martingale. This X hash will correspond to everything that will be a pure jump martingale in the limit. But of course, in the discrete time setting, they are both pure jump martingales. That cannot be anything else. Okay, so you have the C process with which you are integrating, which is like the quadratic variation of this part, which is Kadlag increasing and predictable. You have a terminal condition. You have a function here which, okay, depending on exactly the BSDE we are looking at, it can also be stochastic Lipschitz. So for some settings, it can be stochastic Lipschitz. And then the equation looks more or less as before. You have the terminal condition, you have the finite variation part, which you're integrating with respect to this process. And then you have your martingale part, and your martingale part, it decomposes to this like Ito integral with respect to, in the limit, the continuous martingale part. You have the integral with respect to the pure jump martingale. And then if you don't have a martingale representation or a predictable representation, then you have the rest, which is the n is orthogonal to the previous two parts. Okay. Yes. Yes. Yes, this is a pure jump. This is a random measure of the jumps of X of this process. So let's say of your driving martingale. But it is orthogonal to this part in the appropriate sense, right? Let's not discuss this. So I mean, I have a huge carpet in which I'm hiding technical details, right? Okay. I mean, in the limit, this will go to the continuous martingale part, and this will go to the pure jump part. But when you're doing discrete time, they are both jump like pure jump martingales, but they are orthogonal in the appropriate sense. Okay. Clear? No, I mean in the setting you don't. This process does not have the predictable representation property, so you cannot span all stochastic integrals by just looking at these two terms, and then you need a term which is orthogonal to these two in order to complete the space. Yes. This is like the stochastic integrals which are not spanned by these two martingales. It is just an orthogonal component. Okay. Yeah. Okay. You can also consider, I mean, for the second part, for this propagation of chaos part, you also need to consider like mean field systems of BSDEs. And in this general setting, they take this form that you have more or less what you had before. And then for the mean field system, you have interaction through the empirical mean between all the components in the system. And you also have a McKean-Vlasov BSDE, which are independent copies of the same BSDE, where now instead of the empirical mean, you have the drift is affected by the law of the process. Okay. Yeah. No, it is not. No, it is not a special case. It is not necessarily one-dimensional, but they are not interacting. They can interact, but not not in the mean field way. Okay, I have never thought about this, to be honest. Let's put it that way. I don't think there is an easy corollary in which you would go from this one to the existence and uniqueness for the next stage, right? Because here you don't have any explicit. Okay, I don't know. You could say that why. I don't know an easy way to go from the one to the other. Okay, so these are the type of BSDs that we want to consider. And okay, the method of proof for existence and uniqueness, it basically follows this very nice paper of Oil, Caroui, and Wang in what our French friends call this little red book. And the main ingredients is that you need suitable null spaces. You have some lemma generalized inverses, which is important for us since we have this, since this process is not continuous. This is something that you need. It's a technicality. You need to prove a priori estimates which are fitting to your BSDs, and these are somehow different between, like, let's say, the classical case and the mean field or the McKean-Vlasov BSDs. Exactly. I mean, here you would also need an assumption which involves these measures, and then so you would need something like a Lipschitz assumption on the Wasserstein space for these measures. Okay, and then, well, everything fits together by some fixed point argument. Okay, fine. This is existence and uniqueness, and now we would like to go to the stability results, which is, I think it's probably the most interesting part of this talk, or hopefully. So again, you consider the BSD of this type. The green part are the data that you are given. The red part is the solution. And what we call stability is any result that tells you that if you have convergence in the initial data, so if you have like a sequence of data and these are converging in an appropriate sense to some limiting data, you would like that the solution corresponding to the sequence of data is also converging to the solution of the limiting data. Is the statement clear? Good. Okay, now the technical tools are some, there is some very nice papers of Meman where he was proving some stability of Dubh-Mézières decomposition. So what he was basically proving is that if you have a semi-martingale or a special semi-martingale with this decomposition into a martingale part and the finite variation part, under appropriate assumptions, which include the extended convergence of these processes and quasi-left continuity, this is like the most understandable parts. Then he shows that, you know, the semi-martingale will converge to the limit semi-martingale, but then also the martingale part will go to the corresponding martingale part and the finite variation part to the corresponding finite variation part. Okay, so this is nice. And then we extended this result from Dubh-Mézières decompositions to martingale representations. So, okay, what we want to do is the following. You assume that you have some square integrable martingale which is quasi-left continuous. So in the limit, you have a continuous time process, and which has a predictable representation property. So in the limit, the end part is disappearing. Okay, and you assume that this is converging in an appropriate sense, and then you do the following. Okay, you also have some random variables which are converging, and then you do the following. You construct a martingale by taking the conditional expectation of this random variable with respect to the filtration. Now you know that the random variables converge, and you know that the filtrations converge. So this, what you have constructed, is going to converge. Now, if Y is a martingale, it has a martingale representation again, so you can write it as, let's say, an integral with respect to a continuous martingale. Let's say this not carefully. You have an integral with respect to the pure jump part, and then you have the orthogonal component. And what we can show is that this is converging, then, okay, the initial values are also converging. And then you can show that these two integrals together are going to converge to the corresponding limit. And then the orthogonal part is going to converge to 0 since you have the martingale representation property. And the structure of the proof is basically what appears here, right? You get this convergence for free, which gives you also this convergence for free. And then all the work is to show that the orthogonal part is going to converge to 0 because, well, once you show this, then this also has nothing else to do than it converts to this corresponding limit. Okay. We can currently not prove convergence to something other than 0. So here the assumption that it has a predictable representation property in the limit is crucial. Okay, if this limit is non-zero, then we cannot show anything. And we can also not show that, you know, this part is going to converge to the continuous martingale part, and the other part is going to converge to the purely discontinuous martingale part. And I think this is also not possible. Okay, this is what our friends from statistics say, that if you have a discrete time process, you cannot measure what is exact volatility and what is jumps. Somehow the manifestation in this type of limit theorems is this here, that you cannot say that, you know, they converge as a sum and not as two separate parts. Okay. Good. And then, well, I mean, if you are armed with this result, then, well, basically what you can show if you go now to the BSDE, you have basically proved, well, you have basically proved that this martingale part is converging to the limit that you are interested in. And then you just have to put some work in order to show that this finite variation part is going to also converge to the part that you want to converge. Okay, so stability for BSDEs then follows, okay, with some technical tools, but then it's not such a surprising result anymore. And then you get the same thing, right? That the solution of the BSDE goes to the solution. The sum of these martingales will go to the sum of these martingales, and the orthogonal component is going to converge to 0. Because again, you need the martingale representation property in your assumptions. Okay. So the structure of the proof is the following. So you know that your data is converging. So you have a sequence of data that it is converging. And you would like to show that the sequence of solutions is also converging to the corresponding limit. And the way to do it is the following. You're going to use the Picard iterations for these solutions. So on the horizontal side, you just use the existence and uniqueness basically to show that point-wise these Picard iterations are going to converge to some limit. So for every solution, for every set of data, you show that horizontally the solution is converging point-wise to the limit you want. And then you have to put some work in to show that this sequence of Picard iterations is going to converge to the limit Picard iteration in the appropriate way. And then you use this Murau's good theorem to conclude that then the solutions are also converging. Okay, questions? Good. Now, let us return briefly to this, to this mean field and this McKean-Vlasov BSDEs. So the propagation of chaos result is telling you the following, that if you have a system of like an interactive system of equations, which is interacting through the empirical mean, which is this term here, then if you increase the number of players, this is going to converge to a McKean-Vlasov equation, where now you have just independent components of the same process. And this component is affected only by the law of the solution itself, and it is not interacting with any of the other components. Okay, so we could prove, we could prove a result, a propagation of chaos result for BSDEs at this level of generality, not for semi-martingales now, only for Levy processes. And it is basically telling you that if you have a system of mean-field BSDEs, then it is going to, okay, you have a system of mean-field BSDEs and n McKean-Vlasov BSDEs, then you are going to get, first of all, what we call this propagation of chaos for the system. So you get a convergence of these average versions. And then after some work, you can show really what everybody calls propagation of chaos, that the McKean-Vlasov solution is corresponding to the mean-field solution is corresponding to the McKean-Vlasov solution, and the same is true for the Z integrator, the U, and the orthogonal component. Okay, so really the whole BSD is corresponding, the whole mean-field system is converging to the McKean-Vlasov equation. Okay, and the nice thing, in my opinion, is that we have also a new method for proving this type of results. And we don't use the classical tools, which is coupling and change of measure and things like that. We need basically three things. You need the immersion of filtrations, the a priori estimates, and some estimates for the Wasserstein distance, and then obviously the law of large numbers, which is essential in all this type of results. Okay, and again, if we go back, in order to prove this propagation of chaos, what you would like to do is you would like to estimate the difference between this equation and this equation here. And the first thing to notice is they are not defined on the same filtration, right? This is the equation, the mean field equation is defined on a filtration which is obviously larger since it involves all the martingales and all the particles. But thankfully, using results from the immersion of filtrations, you can show that the solution of this BSDE remains a solution in the filtration where this is well defined. So then you can use them and you can do it. You can do calculus basically on the same space. And if you can do calculus on the same space, then the a priori estimates of the BSDs, they are becoming handy. Okay. And finally, so the final results, so coming back to the initial slide, so you can wake up now. Again, stability means that if you have a sequence of solutions which is converging, if you have a sequence of initial data which is converging, you want the solutions to converge. So here we consider a sequence of solutions which is coming from a system of mean-field BSDs which is driven by a discrete time martingale. This is what these things are corresponding to. And okay, the way you can prove that this is going in the limit to a continuous time McKean-Vlasov equation is using the propagation of chaos horizontally. So each of these, so the Picard scheme for this system of mean-field BSDEs is going to converge to the Picard scheme of the corresponding McKean-Vlasov BSDE. And then if you have a stability result for the McKean-Vlasov BSDEs, which we can prove analogously to the previous one, then you can get somehow like the diagonal convergence, right? That you can start from something which is discrete time and mean-field, and you convert to something which is continuous time and McKean-Vlasov. Yes. Okay. Yes, that's a very exactly yes, the first sorry. So the last index is the number of players in, or the number of particles in the mean field system. I think the first index is the datum you have, and the middle index is the Picard iteration. Index is always the same. Okay, then I said something wrong. No, it is the last one. Okay, no, I get it now. So the last index is the number of players. The first index is your data, and the middle index is the player that you are looking at. And you're always looking at the first one since they are IID or the players in the limit. Yeah, but thanks for asking. Okay, so conclusions or open problems and references. I think we have a very nice machinery for proving abstract convergence results from like discrete time to continuous time. What we don't have is numerical methods, but since we are in a conference for stochastic numerics, this is a call to the smart people in the room to maybe, get involved or discuss with us. And references, I mean, the first three are the papers with Alexandros and Dylan, which have been published already, and the last two is the papers with Alexandros and Stefanos. The first one is about existence, uniqueness, and propagation of chaos, which is already available. And the second one about the stability for the propagation of chaos is forthcoming, but this I'm saying, and it is really true. So we are just working on the introduction, and then we upload it on the archive. So well, thank you for your Thank you very much. Questions? I heard that.
Thank you very much for the nice talk. So would you go, is it possible to go from, say, convergence of sequences to have stability estimates, like the norm of the perturbation in the output being controlled by the norm of the perturbation in the input?
Yes, this is what this is what the a priori estimates are doing for you.
Okay.
Right. So 1 second. So the a priori estimates are basically allowing you to control the things in red using the things in green.
So isn't that worth showing essentially? Show the
yeah.
Showing the multiples of two.
Okay. You mean include them in the slides? Okay. Okay. In the next iteration, I can do that. Yes. Okay. Yeah. That's a very good point. Thanks.
Thanks a lot, Antonis, for the nice talk. I have two small questions on this stability result where you have this convergence of the continuous plus jump part.
In the end, you mean all?
Yeah, about the sum, right? The sum of the two components, but
here or sorry. Now I understand.
yeah,
yes.
This one.
Yes.
This would make sense, right? Because you could get diffusive behavior attained from jumps, right? So you could approximate diffusions by jump processes.
Yes.
But is this included in your set of assumptions?
This is a pure jump process, right? So a discrete time process is by definition a pure jump process.
Okay.
Right, and this is going to converge to a diffusive limit.
Okay.
What you cannot do is you cannot disentangle the two parts.
I see.
So you cannot say that this is going to converge here and this is going to converge here, but you only know that the sum of these two is converging to the sum of the two in the limit.
And related to that, if you could you allow some diffusive approximation of jump limits if you extend the topology instead of working on J1 topology, maybe I don't know, the S topology of Jakubowski?
I would think yes. So at some point we were also thinking about this, so try to approximate with some Brownian motion in pure jump process. I think it works modulo some technicalities.
Okay, if there are no questions from the audience, I have a small question. Is there any way to prove this kind of results using adapted topologies? It's like adapted Wasserstein topologies.
I don't know on top of my mind. I would have to think about this. So I'm not even. So this adapted Wasserstein topologies is what Matthias Spiegelberg and
Yes.
have been working. Okay. I'm not very familiar with them, so I don't want to say anything.
Okay, so thank you very much for this very nice talk.